All right, so let's try this 32-bit Linux exploit, ED440. So the first thing is get the ARM32 emulator going on that Ubuntu machine. So I'll start it here, and it's same old password. So this is Raspbian.
Which page you are in?
ED440.
Oh.
Here? Yeah. All right. And I'm going to need another SSH into the Ubuntu machine before long, so I've got that set up. All right, so Pi and Raspberry. All right, and uname minus A shows that we have ARM32 which is a 32-bit ARM. All right, and so I want to connect to the emulator by SSH so I can use tools like Nano. So you see it has this address, 192.168.122.9. So I'm going to SSH into there. SSH Pi at that address. All right, and that's Raspberry. All right, because this is the console in the Pi, and this is an SSH into the Pi, which will behave better. All right, so we make a vulnerable program, and I've already got it here. Let me just cat it. All right, and this program is a little more complicated than the previous one because the Raspberry Pi, every instruction is 32 bits long, and a lot of them contain embedded null bytes and so on, and it's really pretty difficult to avoid that. So I wrote a program that takes hexadecimal data instead of string data. So you can put in any hex values you want to. So that's what this does. It takes hexadecimal data, 2 characters at a time, and then treats that as a password. Then here's the test password command here is called, and then all done. So it calls, so here it defines space for 10 characters for the password, but then it copies in this raw output from here. And I expected to see, yeah, here we are. There's a global variable raw and hex. It's going to copy the data in created by this program up to 1,000 bytes. So much more than 10. So this is the overflow. it can put far more than 10 bytes into this password. Then it just prints some addresses so we can see what's going on and returns. And so this creates an overflow, and we can use it to take over the box, and that's what we're going to do. So we compile that thing for 32-bit ARM, and I've already done that. So if you run pwd and give it a password of 2 A's, it has to be 2 characters in hexadecimal. Notice that the password is at 35cc. If I run it again, the password is now at a different address. This was BEF6 and this is BEDD. So address space layout randomization is on, and that's bad. That will break my exploit. So we have to get rid of it the same as before in the system. So we sudo su minus to become root, and turn that off and exit. And now it should no longer randomize the location of the password. So this is BEFFF5CC, and it stays at that address each time I run it. Alright, that's important. If you don't do that, the exploit will give you trouble later, of course. So now we're going to fuzz the program. If I give it a short password like 10, 10, 10, 10, which is 32 bits, these are hexadecimal, then that works fine. It just prints all done and doesn't crash. But if I give it a longer password here, then I get a segmentation fault. So that shows the vulnerability, and now you can examine it in the GNU debugger. -q pwd. So I run it, and when it asks, I'll give it that same long password. And it crashes with 1C202020 in the program counter, which means this part of it is what ended up in the program counter. So that's good. Now we can find the return address, and here's where you'll see. All right, so here is the command that calls the testpw function, and when it returns, it should go to this address, 10828. That's the next instruction after it returns. So if we look at the stack at the point of the overflow, we should be able to see that return address on the stack. So if I list the source code from 39 to 46, that shows me the testpw function. This is where the overflow happens. So if I put a break down here at 46, that would be before it tries to return. So I'd see the condition of the stack after the data has put in. So now I run and say yes to run from the beginning, and I give it a short password of 10, 10, 10, 10. Now it's going to run to the breakpoint. Okay, and now I can examine the stack with 10x from the stack pointer. And so here's the 10, 10, 10, 10 I put in, and here's the 10828, which is the return pointer. So you can see this is just like the previous exploit we saw. I have the ability to inject data here, and all I have to do is inject enough data that I overrun the this address, and then I'll be able to take over control of the program counter. So we can now examine an overflow by running with the same long value. So if I run it, say yes, and enter the password, and now look at the stack again. You can see 10, 10, 14, 18, 1C, and this part down here. So it did overflow to this point. And that's how we gain control of the program counters. So now what we're going to do is continue to overflow and inject code over here and jump to it and run it. So we need to make dummy shellcode. To make dummy shellcode, you need two things. You need a NOP command, a command that does nothing and proceeds to the next command, and you need a command that will cause the debugger to break and come back. Now, I found a couple of commands that are good enough for this. This command does nothing. I think it copies a value back into the same register, and I found just an invalid command which will cause the debugger to stop. There wasn't an official break command in the ARM processor, but this is good enough. And so I'll set the program counter to A0, B0, C0, D0, just a valid dummy value. So here's the exploit that does that. Let me get out of the debugger and show you this one. Here's the first exploit that sets it up. Now, something keeps going beep at me. Wonder what it is. This happens to me a lot in these days of technology. Some technical device is beeping, and I have no idea what it's talking about. Well, no clue. All right. Anyway, so here's the prefix. This was the bytes before the bytes that end up in the program counter. Here's the 4 bytes that go in the program counter. Here's my NOP sled, 50 times that 32-bit word that does nothing. And here's my room for a buffer, 100 times that 32-bit word that just causes the debugger to stop and return control back to the debugger because it's an undefined command. So you have the prefix, the program counter, the NOP sled, and the buffer, which is going to be the exploit. And it just prints that out. So you run that and put the output in a file called att1, which I've already done. So if you look at att1, that's the exploit, all that hexadecimal code. So you can run it in the debugger. And run, getting the input from att1. And it runs, feeds in this long password, and if it worked correctly, it's going to put this A0, B0, C0, D0 in the program counter, and you see it does. That's where it stops. This is in the program counter, so that's illegal, and it stops. So that shows that it's working. And you can now examine the stack with ADX at SP to plan the exploit. So here is the preamble stuff. Alright, and anyway, what I want to do here is I want to find some value in the middle of this. And here's one kind of in the middle of the NOP sled. These are the NOPs, these A001s. You want to hit somewhere in the middle of that. This address will do. That'll be a target address to jump to. So I put this in the program counter. It will jump here and do nop, 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 and then run the buffer here. So that's the only purpose of this. Now I have that address, BEFF610, as a good address to jump to. So get out of the debugger again and look at the next one here, which is EX2. And so now I just feed in that value, BEFF F610. You have to put it in with each byte in reverse order. BEFF F610. Then you have the NOP sled and the buffer here. So now this attack will actually execute some code. It'll execute some of those NOPs and slide down the sled, and it will end here when it hits this command, which is 668. BEFFF 668 is where it hits the first unknown command at the end of the buffer. And I should be able to see that address when I run this in a debugger. So I go back in here, and I've already output that program into this file att2. So when I run this, it should jump into the sled, slide down the sled, and break at this point. BEFF 668. And there we are. It made it to BEFF 668, so it did execute some of these NOPs, and hit the undefined instructions and stop. So that's what we want. That shows that I have code execution, and now all I have to do is have some real malware to put there. Now, I didn't put Metasploit on the Raspberry Pi. I'm not even sure it would run. I put it on the Ubuntu host. So you install Metasploit. I used Snap to do it. That worked. And now you can find there are a few ARM32-bit exploits. One of them is shellbind TCP, which is one that will just listen on a port, and by default it will listen on port 4444, so you don't need to specify any parameters if you're willing to listen on the default port. A Discord notification, that could be it. I do have Discord, but I'm not running it intentionally, but I think you're right, it's probably Discord. Anyway, right, so this is how you generate the code. The same as before with MSF Venom, that generates Python code available, and you can just put it in the exploit, and I've got that set up here. So it's cat ex3.py. Oops. All right, what's the story here? Oh yes, that's in my Raspberry Pi. You generate the exploit on Ubuntu and then copy it in. So here's the story. I have the prefix, which is enough bytes to get me to the part that where you control the program counter. Then the program counter has this address that'll jump into the NOP sled, and this is the buffer, which will run, and that should start listening on that port. So it should run. If I run the I've already put that in ATT3, the output, so if I run pwd and get the input from ATT3, it runs, and it continues to run. So it is now listening. So now I can connect to the shell by connecting into my machine. It's now listening on port 4444, my Raspberry Pi is, so I can connect with this command, which will netcat into it, on port 4444. So here I am on Ubuntu, but when I connect on port 4444, I'm now in, if I do uname -a, I'm now in the Raspberry Pi, remote controlling it. And so you can find a flag by looking at the network connections, and so on. You can now execute commands here. If I do who am I am Pi, and you can exit when you're done. So that's a complete exploit, and press enter again to get back to Ubuntu. That's the complete exploit, the buffer overflow exploit with malware on 32-bit ARM. And 32-bit ARM is very much like the Intel processors we exploited yesterday. The string you put in comes before the return pointer, so it's very easy to just put in a long string and hit the return pointer. As we're going to see, it's not that simple on ARM64, but this will do for ARM32. I'll stop this.